a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician.
All right, hello and welcome everyone to Celestial Theodolite update number 36, the big 3-6 tonight. Last week I talked about trying to come up with a better way to word the relationship between the central angle, which is noted as gamma, and the curvature of Earth, which is noted by half gamma. So half of whatever the central angle is also happens to represent what the drop over distance for that particular distance is. So anyway, I didn't get around to the diagrams or anything yet, but our local Canadian correspondent Goose came up with his own explanation and wording and understanding of it, and it was really good. So I thought I would share that, and then I also made a spreadsheet page to show like the notation that he used and show you guys what it represents. So diagrams and stuff still forthcoming, but we will go over this. But before we get into that, actually we can do that after. Remind me, there was some new stars added to the spreadsheet. We'll go over those after the after this. So shout out to Goose. So how central angle theorem combined with the celestial theodolite falsifies a spherical Earth, by Goose in the Ether Cause Discord. This is a rough draft or whatever, so things are subject to change or what have you. And obviously, if anyone has any corrections they want to make, let me get a copy to everyone in case they want to critique it or whatever. So, Sound Theo update 36. Okay, PDF is in the live chat if anyone wants a copy of that. So here we go. So to describe central angle theorem's significance when falsifying Earth's curvature using the celestial theodolite technique. Introduction. Earth is popularly assumed to be a spherical object, and such enters the geometry's domain. Any geometric object must abide by the laws and theorems of trigonometry. With central angle theorem, we are able to calculate the altitude angle that a star must travel in the sky as distance as traversed between 2 points on Earth's surface. Once the central angle is known per the theorem, the angular drop of Earth's surface between those points is exactly half the central angle. And if you guys have ever, you guys have probably heard me talk about this, where I'll refer to the central angle as gamma and Earth curvature as half gamma. That is the, let me pull up a diagram for everyone real quick, so we can all see what we're talking about conceptually. I do have a diagram of that, so that will help. Okay. So this relationship right here, where we have the arc length, this is going to be, what defines the distance. And then half of that arc length, or I'm sorry, you can also convert that arc length into an angle, and that angle is going to be gamma. And then half of that is going to be the drop over distance of that. So in the example of Pikes Peak, where the arc length is 500 meters, the Earth curve of that angular relationship is 200 meters. So there's 200 meters of drop over that entire arc length. That's what creates that. So that's what we're talking about there for the central angle and half central angle. So theorem 1-1 for central angle. The central angle subtended by 2 points on a circle is twice the ascribed angle subtended by those points. And what that means is basically these two lines that are subtending the circle, half of that is the inscribed angle, and that is just it's like a proportional ratio statement, essentially. So that's all that it's asserting, and that's true for let me see, central angle simulator. No, that's not it. Anyway, I'll get a link to a simulator. You guys can play around with it, but basically there's always a proportional ratio established with that. An exciting technique referred to as the celestial theodolite has been generated by Dr. Mike Heffron, where the exact time that a star is occluded by a physical mountain peak shows that the Earth curvature is false. The measurement technique also shows the astronomical refraction, as currently assumed, is nothing more than a myth. Central angle theorem is key to unlocking this understanding. This author hopes to further his own understanding of the implications of the central angle theorem to the celestial theodolite technique by putting in his own words this concept. So the author hopes that that the below will provide another angle to view the concept, which may help others in their understanding. The measurements. On January 27, 2025, the star 39 Aquarii was occluded by Pikes Peak at 1843.07 minus 7 UTC. The observer was located at these latitude-longitude coordinates, and with Pikes Peak located at these latitude-longitude coordinates. The distance between those 2 points on Earth's surface is noted by y sub d for 50,000 meters, and of course, or 50,551 meters. And we, of course, calculate that with haversines by the latitude signs there, or the latitude coordinates. So that's how we got the distance. So y distance is this. Observer at the time of eclipse was at an altitude of XA. So this is observer altitude, XA. And the peak's altitude is noted by XP. And this generates 2 points of interest for angles. The star angle at the observer location, which is noted by theta t, which is 2 degrees and 9 arc minutes. So we're going to be starting off our example here with Pikes Peak for the familiar reference. Now, the true angle to the peak at the star at the peak location is noted by theta little lowercase p. So note these lower cases here because they're gonna change here as we continue. So anyway, that angle is 2 degrees 33 arc minutes. So on the spreadsheet here, the star at the peak location is 233. Star at observer location is 206. So here's a nice diagram that Goose made up here to kind of show what's going on. So we got the expected, let's see, oops. So here we go. The angular, the central angle there, 27 arc minutes. So for that 50 kilometer distance there, you can multiply that out by the radius to get the, or I'm sorry, you can divide it by the radius to get the arc length, which comes out to be 27 arc minutes. So that is the, oops, that is the gamma, that is the central angle. And then half of that is the drop over distance, that half gamma. And on the spreadsheet here, that's noted by terrestrial drop 180, which is, actually I can probably remove that. Anyway, globe drop here, which is noted by the half gamma. And that's just 180 times the distance over 2 pi r times the radius to get the arc minutes for that. And then, of course, you can convert the arc minutes through either a tangent function or multiplying the Sagitta out by 4, and that'll give you what the drop over distance would be, which is 200 meters. So that's what we're looking at here. So we have 2 elevations overlaid on top of one another. So for flat Earth, it's noted in the light brown here, globe Earth in the darker brown. Star's position at the times of occlusion, and then with respect to each location for the alignment. All right. Now above, figure 1 shows all angles required to apply central angle theorem to show the Earth curve is false. Drawing is to scale relative to itself, so one can easily visualize the relationship of the applicable angles. Calculating the peak angle and applying an offset. The angle to Pikes Peak, which is noted by theta capital P, can be derived using the elevation difference divided by the distance times 180 over pi, or you can do arctan rise over run, and you get a small what's it called? You get a small decimal placage disagreement or whatever, but for the low angles that we're using, they're approximately, it's approximately equal to using arctan rise over run. So to more clearly show the angular relationship, it is helpful to generate an offset, which is going to be noted by theta e, to be calculated using the measured eclipse star at theta peak, which is going to be the star's position at the, with respect to the peak, and then subtracting the two, which is going to look like this. Oh, real quick, we'll read this. So theta p has no relation to planar Earth's common rise over run calculation, even though the angles have a similar value generated using this method. Planar Earth has no bearing on these calculations, but it reveals its physicality through the measurements. So let's see here. So we got theta e equals the star's position at the peak with respect to the angle to the peak that we derived earlier using this here. And that gives us 1 degree and 55 arc minutes. Now, there's like a small difference, like I said, from using arctan rise over run or whatever. So on the sheet, it comes out to 2 for the offset, but using that, following what Goose did for that, it comes out to be 1 degree 55 arc minutes, like it shows in the thing. So this is a new tab that was added called Goose, and this follows the notation that Goose used to derive everything. So as we go through the document here, we're also going to look at the spreadsheet following this. So here in this column, F1, we have the elevation difference over the distance times 180 pi, which gives us the equivalent of rise over run to the peak, which would be the flat Earth angle to the peak. And all these are noted too, so we can read through the notation too to make sure we understand everything or whatever. So anyway, that difference between the peak and the star's true position is 1 degree 55 arc minutes. So same situation that we're looking at here on the spreadsheet. The intersection difference is that. Same for the globe. So for the true position, we subtract that from what they predict for their intersection, and we get these elevation differences. And then the elevation difference of our measurements there is like how much we mismatched on our predictions. In other words, is equal to the half gamma, and that's going to be extremely significant as we go forward. So it's just showing that relationship. It's like what it looks like in the spreadsheet normally and how we've been talking about it. And this is kind of like another way to describe the relationship that I've been trying to talk about. Okay. So we've got our offset. So we first apply this to the peak, or from the star's true position at the observer. So we take observer location and we subtract this offset from their location. So on the spreadsheet here, observer location is 206. We're going to subtract that offset to them, and it's going to make it come out to be 204. All right, and then we do the same thing for the star's true position at the peak. So that's going to bring it down to exactly what we would predict for flat Earth. Now, I know like the immediate contention would be like, aren't you just, making it line up with flat Earth? The air difference, right, is already there. This geometry already exists within it. We're showing it from a flat baseline, what the measurement looks like in terms of air difference. And then I'll show you what the globe looks like if the globe actually hit their occlusion, how it would be reversed in terms of that air offset. Because we would be off by this gamma amount. This half gamma here is the elevation difference between flat Earth and globe Earth. This is where the significance is going to come from, because how much we're off on here dictates, if we were to use the star's true position at either location to derive a triangle, how much we're going to be off in elevation and distance, using only one of the other known variables to solve for the missing one. So everything stems from this intersection difference. This is the significant part of the spreadsheet. Everything else is just kind of there for funsies. All right. Because everything stems from that relationship there. So an offset corrected, this angle remains unchanged. So the significance of that is, we're just aligning it to a frame on a flat Earth, because as we're told, the stellarium assumes globular geometry for the terrestrial sphere to make the celestial sphere match and all of that. So when we subtract the difference between those two and align the star's position to flat Earth, we're looking at the true elevation difference that was measured, or that was measured at the time of occlusion. Because if the Earth were a globe, these would basically be reversed, these offsets here. Oops. We will continue on. So central angle and measured star angles. We can easily calculate the central angle using the distance from the observer peak. We only need to introduce Earth's radius. So you can do, to get the central angle, you do distance over Earth's radius, and then to convert it into decimal degrees, 180 over pi, and that gives you what would be 27 arc minutes there. So we have that over here in the sheet. Oops. Let's see. This one comes from, okay. The bottom one down here, the straight gamma and gamma underscore p are going to be derived from central angle theorem using Earth's radius, and the gamma m and gamma just gamma half are going to be derived from just the star's positions. We'll get to that as we continue. So kind of keep that in mind here. So this one's derived using radius. This one's derived using star positions. All right. Each location has a corresponding angle at the time of occlusion. In other words, January 27, 2025 at the time of occlusion, 39 Aquarii had an offset corrected angle equal to theta t at the observer location. So that's the angle at the time of occlusion. So we have that noted here on the sheet. Or no, that was for the globe, sorry. That's for the observer centric. And that gives them the 20, or what was it? That puts them down at 204. Okay. Oh, yeah. It also had an offset corrected angle equal to theta p at the same time. So gamma m is equal to the star position, the corrected star positions minus each other, essentially. So if you take the star's position at the peak minus the position at the observer, you get 27 arc minutes. And that's what we show here with this relationship. So basically, showing that when we subtract this offset from both, we're preserving the central angle. Like, we're not changing anything. We're just looking at it from the flat Earth perspective, essentially. So you can think of it kind of like a reference frame offset. So the difference between flat Earth and globe would be that half gamma. So anyway, you can derive that from the star's positions, even if you don't correct it here. Like if you didn't offset it, it would still be the same. And I have that here in the sheet here. So the raw natural angles at the time of occlusion, as reported from stellarium, if you subtract these two, they come out to be 0.45, which is 27 arc minutes. And all that is done down here in this section in the spreadsheet for star drop and delta star drop. All that is basically just comparing the math predictions versus where they turned out to be, just to make sure everything lines up in stellarium and whatnot. So all that's done there. It's just showing that relationship. So it's very important to note that the above angle was calculated using the star's true position and the angles at the time of the occlusion for the peak and the observer. The full angle of the star traveled is equal to the central angle as required by the distance traversed between the observer and Pike's Peak. So that's the relationship of, like, the star's ground position change over that distance is equal to that angular amount, which is the elevation difference uh, between flat Earth and globe. So and then that because of that drop to the peak, that alignment for the observer centric prediction, that's why it comes at an earlier angle, because it's already lower at that observer centric angle. It's already aligned geometrically. It doesn't have to be aligned with the peak on a flat Earth to get occluded, because the Earth is a globe, right? So there wouldn't be. Anyway, we've been over this, so it's just going over how that works out. So the central angle in spherical Earth and gamma and half gamma offset feature refraction and featuring the refraction myth. All right. A natural consequence of a spherical Earth is the drop in ground level over distance. Given central angle theorem, the angular drop between the peak and observer looks like this. The gamma between peak and observer is equal to, noted by gamma p, is half gamma. So you could just divide gamma by 2, and you'll get 13 arc minutes in this case. To calculate our angle on the spherical Earth from the observer to the peak, to get theta g, right? If we were going to predict what the geometric angle to the peak is for an observer on a globe 50 kilometers away, you could do theta p minus gamma, and that's going to give you 217. And we have that here in the sheet. So remember, theta p is going to be the corrected flat Earth star position, or rise over run to the peak. And if you subtract 13 arc minutes from that, you get 217. You get what the globe would predict for their geometric angle. And let's see. Okay. We can also calculate it by adding it to the star's position as well. So if we take the star's offset corrected position and add the 13 arc minutes to it, we get 217. So that's also in the sheet here. Oops. Noted by, I think it's this one, yeah. So here we just add it to the star's true position that was corrected by the offset when we aligned it to flat Earth, and it comes out to be 217. And let's see. And at this point, we should seriously be considering if astronomical refraction and its stated role of lifting the stars into the apparent globe star position is reality. It is reasonable to state that at this moment, astronomical software uses a variety of refraction formula to generate what's referred to as the apparent position. The sole reason is claimed that the apparent position of the star at the observer is the altitude due to astronomical refraction. We have proven that the astronomical refraction can simply be calculated by using basic trigonometry. No curve fit ad hoc refraction formula required. 6. The illusion of globe drop. A celestial theodolite timing will have angles that correspond to theta t and theta p, with the difference between the angles of gamma m, which is just that half central angle, equal to the angular distance between Pike's Peak and the observer, noted by gamma. On a spherical Earth with the ground sloping away from the observer at all times, the star eclipse timing must have an offset from the full central angle, gamma, by gamma p, which is that half angle, or half the central angle, essentially. If the timing does not correspond with gamma plus or minus gamma p, we are then left pretending that during the eclipse from the observer position, we see the mountain peak occluding an apparent star or refracted position, which we have shown is, which is impossible, as we have shown with the myth of astronomical refraction, geometric construction lacking a physical tie to reality. Denouncement. To date, there have been many well-documented celestial theodolite timings, and the catalog continues to grow. Thorough, in-depth analysis has been performed on most. This author encourages dear reader to investigate this young technique. Many other measurements are still yet available, and we are only begun to scratch the surface. If you live in a suitable region or you're going on vacation where there's a suitable spot to make celestial theodolite measurements, be sure to bring a recording device that's synchronized to GPS time, uh, or at minimum, a pair of binoculars and a stopwatch. All right. So that is Goose's conclusion on central angle theorem and how it relates to the offsets and what we did there. And like I said, I would show you guys what it would look like if globe. So if globe, the occlusions, like I said, would be reversed, or this difference would be reversed here in terms of us being flat Earth being off by 11 versus the globe is off by 11. So what it would look like if the star were aligned on a globe, we would have, where's it at? There we go. So the offset angle there, the flat Earth is now off by that elevation difference, which is the drop over distance. Now, in terms of how everything worked out, all the ways to derive, the predicted angles and whatnot remains exactly the same, except the offset difference now, because it's anchored to the observer-centric position that the globe predicts. Excuse me. The offset to the flat Earth frame, basically the peak, would be 13.5 arc minutes. And that's what we show here. And then by correcting all of that, you get all the corresponding angles and everything back. So like I said, the arc length and gamma are preserved. There's no change in that. We're just looking at it from two different reference frames essentially, and the difference between those reference frames is the half gamma amount. And when we go through the spreadsheet, every single measurement, never corresponds to what the globe predicts. They're always off by essentially like 80-90% of what they predict as curvature. And then we get left over with the difference for the gamma, because it has to be, it's shared between us. So that is where we are at on articulating that and showing that aspect of it. Does anyone have any questions?
Rulips wants to ask a question.
Oh shit! Yeah, 1 second.
Does
Go ahead,
Alan have you
Riv.
turned down? Probably.
Yep. Yeah, go ahead, Riv. What's
All
up?
right. So on a globe, right, the mountain will be lower because of drop due to curvature. So, question is, would a star occlude later on a globe or earlier?
Earlier.
The globe spinning, Rulips?
Yo, 1 second. Rob, that's not important. It would occlude earlier because the star's true position would already be geometrically aligned with that position before it is with respect to the peak. Did you get the thing that I sent you when I went into Stellarium and showed all the positions?
Yeah, like honestly, I honestly don't care what your answer is if it's not, if the answer isn't later, because it shows everyone how stupid this is.
Okay.
That's the point.
So when I go into Stellarium though, and I show the angle being aligned at an earlier time, you're just like, no, that's stupid. And then like you wonder why you're muted here. You just argue from rhetoric. I showed you why it's earlier and you said, I don't care, that's stupid, instead of going into Stellarium and verifying it. So then anyone that repeats your argument would also suffer from the same issue.
You don't really honestly believe that, do you, Ruhif? Like, I don't care what his answer is, even though you asked a question. So what was the point of you asking the question?
To show everyone else how stupid it is.
I think you're showing how stupid you are.
At 8:42:04,
he's
the
just trolling
star.
all of us.
Hold on 1 second, Rob. At 8:42:04, at 8:42:04, I'm sorry, 18:42:04, the star is geometrically aligned with the peak and the observer. It's the observer-centric position prediction, right? You don't want us to go and look at it from the peak or whatever. That's what the observer predicts. And look at that timing, exactly what is shown on the spreadsheet.
Let's say the mountain's 5,000 feet or whatever, and the star occludes. And then by pure magic, I happen to, I don't know, reduce the mountain by 1,000 feet down to 4,000 feet. Would the star occlude later?
Well, let's go with reality and the actual example of this playing out instead of weird hypotheticals. So
The answer is yes, Alan.
so,
The end.
so in reality, the globe has a geometric alignment at 842 or 1842. That's a fact. That's literally in here. You can go and look at the alignment from the observer location at that time. If the Earth isn't a globe, there wouldn't be a later timing for the occlusion. What angle is it lining up with to occlude, other than the rise over run to the peak?
I mean, didn't you say yourself, Ruhiv?
Which is why that's why this intersection difference comes out to be the drop over distance, because there isn't any.
Yeah. Weren't you? I remember in the beginning, Ruhiv, you were like, "Yeah, no, the angle should be 217 and 219 if you want to include terrestrial refraction." Remember that?
219. Yeah,
Yeah.
219. Yep.
So what are you arguing against?
Right. Isn't the angle to the peak on a flat Earth like 231? It's higher, right?
Yo, but we're considering geometric intersections of the true positions.
Okay, the star is going down, right?
In its true position, intersects with the mountain. Correct. That's why it aligns earlier, thus the earlier occlusion. It intersects geometrically earlier.
Jesus. Well,
I mean, you're laughing is stellarium wrong?
If anyone here is rational, can realize how stupid that sounds, if you don't realize how stupid it sounds, then you're completely lost.
So what is the angle supposed to be at that time?
As we look at the angle at the time of occlusion. Or no, I'm sorry, that's not the angle at the time of occlusion. As we look at that is for it being aligned at 217. Sorry, that is it. So yeah, being aligned at 217 true position, that's what time it would be. So you say
earlier than 1843, right, Ruhiv? Yeah, that's right. Yeah, I'm just an idiot. Yeah, no problem, Ruhiv. Thanks for contributing.
All right. Does anyone have any questions on the central angle gamma relationship or anything like that? Or does anyone is it not clear about the geometric alignment for a globe predicting earlier?
Coco said there's no issue with Ruhiv's question, but it's like it literally shows it right there in Stellarium that if you were to match the angle that would be predicted by the globe, it would have to be an earlier time, unless you want to throw out Stellarium.
Oh, do you really want me to look at it? Really?
I made it specifically for you. I made this whole page just for you, linked it to you like a month ago on Telegram. So
show me in 30 seconds.
I got a better idea. You read it on your own and catch up and then come back. Or just open Stellarium and go to this timestamp. 1842
Where's the observer?
At the observer location.
At Mike's house, yes.
Cool. Yep,
use the staple original 231. You say on the globe it should be 217, right?
Yes. So it's higher on the flat Earth, yes. and the star's going down,
Talking about the
Right.
geometric intersection,
right?
right?
Uh-huh. Yeah. So
It-
in
whatever intersection, yeah.
Stellarium, for the angle to actually be 217 to match your globe prediction, it would have to be at 1842.04. But in reality, the occlusion happened later.
Right. What time would it happen on a flat Earth?
I'm not sure. What does
Earlier.
it say, Alan?
Ask the
What
question. I
No.
have
time
it
does
right.
231 happen?
I have it right here.
No, 1843.
1843 is when
Show
it would
that.
happen, and it got it. What's that,
Show that in Stellarium.
dude? It's on the page that I sent that you never looked at.
Yeah, the thing that you're like, oh, I'm not going to look at it.
Oh, that's that's a British accent, Beast. That's terrible.
Yeah, it's about as good as your refutation.
Right. My refutation is simply to point out the simplicity of a star going down will occlude later if the mountain is lower, to show everyone here that whatever bullshit theories you put around it amount to shit, right? That's all my point is.
I'm mistaken, but is the star on the globe not going down, but the ball is rotating, bringing the
Sure.
mountain up to the star, not the star going down to the mountain?
Well, you could
Sure.
Thank you.
it could be either way, and the result of what we see would be this, like the elevation difference created would be the same. So that, like, that part isn't necessarily important to quibble about, but however you can conceptualize it the best that works for you is the most relevant part, because it would be the result that you would see would be the same regardless of how you say sky moving or ball moving.
Who was it the other day that asked, that wanted to clarify whether I was muted on these updates, Celestial Theo updates?
Couldn't tell you.
Doesn't matter.
Doesn't
Anyway,
matter. You don't want to
Cor-
look at it anyways.
Correct. But so, and then what's really funny is when I replied to that guy who asked that, I was like, yeah, because he doesn't look at anything, doesn't actually engage with the argument and reduces to rhetoric. Like, we're looking at the geometric alignment at the time, and you're like, but no.
how about I share my screen and we'll just fuck it. We'll do it live.
Bro, I'm already sharing my screen. I've already done this.
Okay.
It's happened live right now in the chat. You can see the
Okay,
screenshot.
so I'll put Stellarium. Where are we? Let me get set up here a bit.
You can't be right, Alan. You're a flat earther. Like, what the fuck?
Oh, there is that. Yeah.
Yeah, that does kind of follow.
I got you, dog. We're opening the Stellarium right now.
18, 27, 25. Oh, that's
Okay,
right. You
let's
used
see.
the non-canonical example, didn't you? Can we use the 31st of January? Yeah.
Oh, I have the other ones. Dude, that doesn't change it at all. I added the other ones to the spreadsheet.
Non-canonical? What do you mean?
Dude,
The
there's
original.
like a first one or whatever, and the one that I have that I added to the sheet isn't the first one or whatever, but the angles are all, so like there's three different ones to choose from here. Do you want 39 Aquarii moon? Do you want 30, or do you want the other 39 Aquarii? Like, which one do you want? It doesn't change it by anything that's different at all. All of these are going to be the exact same.
Hold on.
Like, we have the timing
like-
differences for each one.
Yeah, like, which one do you want to use, bro?
So
Hang on, I'm just taking
anyway,
some screenshots. 1 second.
yeah.
The Control S in Stellarium, I think.
Yeah, Ruth, I'll just save you some grief here. Basically, the whole gimmick boils down to they ignore refraction. When they use their own numbers and include refraction, the globe's like 4 times more accurate than the flat Earth.
Oh yeah, I know.
That,
Yeah.
that's the whole thing,
Well
yeah.
aware. Yes.
Yeah.
Buddy,
So
when we go to
231.
different peaks, it's predicted that it's still over it, or sometimes it'll be under it. Like, we're not ignoring it. There's no gamma relationship, like, in terms of how much you guys are off. There's no relationship to that in the amount of refraction. It's inconsistent across all measurements. But, like, so again, reducing the conversation to rhetoric and refraction doesn't mean anything. We're
Those
actually in the middle of
two-
discussing a far deeper issue, which is the occlusion differences and not looking at someone's actual argument for months and then coming on a live stream and then arguing against it. Like he's actually going through the process right now as if he's going to get a different time.
Oops.
Share your
All right,
screen,
post in the
Ruhiv.
chat. Oh, I've put the picture in the chat, screenshots in the chat.
All right, what do we got?
All right. First one is 231, 217. 217 happens at 6:26, 23 seconds. 231 happens at 6:25, 6 seconds.
You put 2025 Julian Day. Yeah, but that's not when it actually occurred.
I'm showing that the occlusion happens later on a globe. The star's going down, the angle's lower.
Where's the angle? Hold on, let me see here.
This is fucking trivial. The fact that
So
no
it's
flat earthers are
trivial that
calling
you
out on
didn't
this shit.
even. It's so trivial you didn't even look at the response. So
Right, because
Bro.
it's trivial.
Bro,
And you're not explaining yourself because I don't even understand what you're talking about. And you're calling everyone names too in the room.
Right. The screenshots, right? When the star is at 217 geometric, it's 6:26:23, which is a later time than when the star is at 231, which is 6:25:06.
Yeah, the argument's pretty simple. Is globe drop makes the mountain lower visually, so the occlusion will happen later. That's his whole argument.
yo, you aligned it from the
Very
same location, not from the peak.
Right. You said it was from the Heffron's house as well. You or Beast, someone said it.
The globe predicts from Heffron's house. We predict from the peak alignment.
That's silly.
Yeah, you keep saying that, but then you show up and then not represent our method and act like you have a different time. Bro, that's
No, I've represented your
insane.
method. Let's do Jesse.
Not
Let's do
at
Jesse's
all.
Blinn Peak.
Bro, you didn't represent our method at all. We predict from the peak.
Let's do Blinn Peak.
hold on, go to the
Are we gonna
peak. Hold on,
Dude,
take a screenshot and go to the peak.
Hang on. Let's do Jesse's that one. Jesse. Is that it? There you go.
Jesse's is particularly damning because the refracted position that you guys like to use for the position predicts that it would already be 2 arc minutes and 40 arc seconds over the peak. So almost 3 arc minutes over the peak already at the time that it emerged.
So I've posted
So-
in the chat the screenshot of Jesse's observation, or one of it.
Mhm.
So the raw FE angle, 54 minutes, 34 seconds. The Cell Theo angle, or the Heffron angle, 41 arc minutes. So the Cell Theo is off by what, 13 and a half arc minutes.
Look
That's
at
not very good.
our geometric intersection differences for true position when the star actually emerged after traversing the full arc length. So we have
13 and a half minutes, a win for the celestial theodolite.
22 arc minutes is off by the globe. We're only off by.
No, you said the globe
dude,
does it from Heffron's house.
First of all, don't interrupt me in the middle of talking. The globe we're discussing Jesse's measurement now. From Jesse's observer location, the geocentric position of the star is off by the peak by 22 arc minutes. We're off by 12 arc minutes. The difference of our measurement, like we've been discussing this whole time with the central angle relationship, is what's predicted to be drop over distance. Now, for this one in particular, the true position difference is actually a little more than the what do you call it? The drop over distance that would be predicted, right? But you guys are double that, and you still didn't emerge from the peak with all 25 arc minutes over fraction you guys were still you guys were predicted to be 2 arc minutes and 40 arc seconds over the peak already. So almost 17 real seconds earlier on an occlusion. It has nothing to do with the offset. The offset between us here on the intersection. Hold on one second, because this is extremely important. The intersection differences between us have nothing to do with the refraction amount. Every time you go through this, they're inconsistent with the offset. It has nothing to do with it.
There's no
When you
correlation,
don't
Go
do-
ahead.
essentially.
Go ahead.
All right, I've posted another screenshot in the chat. When you don't do stupid shit like you guys do, the error between the prediction and the actual is less than an arc minute on the
Okay.
globe.
When you say you guys don't do stupid shit like that, right? We're checking to see if our crosshair is aligned with the star's true position, because that's what would actually cause an occlusion. Now, if you call that, just calling it stupid shit is just pure rhetoric. What are we supposed
Okay,
to
then
compare
don't
it
put
to?
your prediction, your strawman prediction, on us. It's not what the globe predicts.
Buddy,
Stop doing it. You've been doing it for a year now.
the globe has a geometric alignment at an earlier time. That's it.
Oh my god.
And in Jesse's case, it would be reverse because it's an emergence. So,
Right.
but in any case, still the same situation.
Yeah.
You say that's
The
not what
mountain's
you
lower.
say that's not what the globe predicts, but you won't even acknowledge our method. You actually went to Stellarium and lined up the fucking true position at 2:30 with from observer location. That's crazy. And you talk about that's not what, and you talk about that's not, and you talk about what you say that's not what the globe predicts, bro. That's not what we predict. That's not our position. We're checking to see if our crosshair and star are aligned. That's what actually causes an occlusion. That's what the whole thing's always been based on.
Okay, let's get all scientific. My independent variable is the height of the mountain, be it a globe or a flat earth, and my dependent variable is the time. That's all I changed. So I changed the height of the mountain. So it sets later on a globe.
What?
So you
why
did.
didn't you put the observer
hold on
the
a
mountain
second.
peak?
You did a completely different geometric alignment. That's not our method at all.
I'll put it anywhere.
Where do
you want the observer?
Bro, that's a different thing. You can put it wherever you want. That's not our position.
Cool.
We don't make an observer-centric position for the alignment. We need the star to be aligned with the peak and for there to be a congruent triangle. What you're doing has nothing to do with us.
Right.
Righto. And for us, right, our independent variable is the distance and elevation to the peak relative to sea level. And our control is the known mountain elevation. And the dependent variable is the occlusion angle, the time of occlusion. So if you want to use our method or like describe what we actually predict, you need to have a geometric alignment from star to peak to observer. And the only way you could do that is by checking at the peak location or by adding the arc length back to see what it would be at that location.
I've done your method and I've posted it in the chat again, and it's shit. It's off by 13.5 arc minutes.
That's how much the globe's off, dude.
No, it's not. Not when you do.
Not when you self-reference the globe, dude. Thanks, Roof. It's been a real gas.
The globe, and you've done it for a year. It's embarrassing.
It's embarrassing that I have the stellarium angles up of what the observer predicts for a geometric alignment for their congruent triangle from star to peak to observer. It's embarrassing that you won't do the same for us or acknowledge the difference and just come here to argue rhetoric and say that we're strawmanning the globe.
You are strawmanning the globe. I've done your method. The results are shit. The results of the globe when you don't strawman it are very accurate. And it's been the case since this shit started a year ago. It's embarrassing. You guys got, what 36? 36 updates.
Dude.
Anyway.
Then why are you
That's all I
here?
can say.
You never address the geometric alignment, and the only time you've ever even attempted, which is just now, you referenced it from the wrong location on purpose.
Then put them on the mountain. It
I
doesn't matter
did.
where they are. If the star's going down, it's going to set later on a globe.
If it's not geometrically aligned from observer to peak, then there's going to be a line of sight to it, and it's not going to be occluded. And that's actually what's observed. That's why there's a timing difference that's created, because you already
Yeah,
had a
but
geometric
it's
alignment
trivial.
from star peak. Dude, it's so trivial that you can't acknowledge it properly.
This is
It's
actually kind of
trivial that a
wild.
star
How do
going
I
down
how do I
is
check
going
if
to
my
set behind a lower target later.
how do I check if there's a geometric alignment to my crosshair from my location?
But you can't. You're looking through an atmosphere.
What?
All right, dude.
You can't.
Well, funny story. You can just reference where the star would be at that location by either using your favorite astronomy software or by adding the arc length back. So,
Yeah, I mean, if you already have a complete globe model that has proper three-dimensional locations for everything, you can use that. But like a
oh,
simple, just in
oh,
your own eyes observation, no.
proper three-dimensional locations, buddy. Stellarium uses a unit sphere. There's only angle.
Yeah.
Say
The
the
only
last word
hold on,
again.
one
What was the
second.
last word?
They use my dude
Well,
just
actually,
said.
no. It uses a sphere of 6371.
Well, actually, they normalize it, and it comes out to be 1 or whatever. It's just an angular thing.
No. You're
Okay, one
incorrect.
second.
They
One
have moon
second.
parallax.
Okay.
They have moon parallax, which is topocentric, and you get a up to a 1 degree shift because of the radius of the Earth.
Okay. So they set their unit sphere to 3950, or like essentially 3959, right?
Are you showing something out on the stream?
So
No,
not
no,
a unit sphere.
no. I'm just asking. Well, no, because when you go through their code, it all says that it'll reference a unit sphere, and then it'll say that it's normalizing it. So I don't dispute that they could do a parallax calculation or whatever, but I'm saying everything that I found in the source code was normalized unit spheres. So I'll send my stuff real quick, and then I'll take your word for the
Separate
parallax.
question,
Though.
Separate
Go ahead.
question.
Mhm.
Can you give me a one-line thing about your thoughts of celestial refraction? Like, is it a hoax? Is it sort of, I don't know. Yeah. What's your basic thesis on celestial refraction?
Well, as given to us, it's a computated model fit. So there's that aspect of it. I don't dispute that refraction is a real thing and affects the apparent positions of objects. But to the exact tune in which they prescribe, that comes out of model fitting. So
Okay, but if I can say derive pretty close to Bennett's formula using like the International Standard Atmosphere, what does that mean? Does that destroy your shit?
That would mean that that would lock you into that having to be that amount of refraction, and then that not being measured ever is would be bad. So like
What do you mean not measured ever?
so all the
Not
instances
measured ever.
so all the instances where you guys would predict that you're still above the peak by 2 to 3 arc minutes or already below it, you would have no way to you would be fully locked in at that point. So like it would be indifferent to me because in the measurements it doesn't show any relationship to the refraction amount. Like even if you could reproduce it, calculating it off of first principles, that amount is never present in any of the measurements. So it wouldn't affect me at all. It would be more damning for you guys.
I can only assume that you're doing stupid shit again.
Man, dude, I'm not going to be talked to like that, bro. That's insane.
Okay, be cordial, dude.
You assume I'm doing
Why
stupid
can't
shit?
anyone-
We have intersection differences that we go over every week and talk about the relationship and go over the refraction argument. We've been doing this for weeks. You show up one night on like I don't know, are you like
for a
bored in
year.
between poker hands and you're just like you just come here to like shoot off the hip like
Bartra. I think the fact that no flat earther is willing to call you out on something as trivial as a star will set later on the globe than it would on a flat earth, just to me tells me you're baffling them with bullshit. No one here would understand it.
No one here. Are you saying no one here understands the geometric alignment for the observer-centric prediction for star to peak to observer would occur earlier when they're looking at a screenshot of it in stellarium from the observer position, looking at the geometric alignment? Like it's already there. What you showed was a geometric alignment from a different location than what we're aligned with.
I'll put it anywhere you like, Alan. Anywhere you like. Where would you like it?
On
And
the
then
peak.
when you say the globe is off, then it must be stupid.
On the
That's what
peak,
you do.
and then you were like, you're off by 13 arc minutes.
Fine.
No, that's the point.
Which is what the
If
globe
you
is off
strawman the globe,
on their
sure.
observer centric position.
If you want to strawman the globe position, go ahead. But the globe is not off by 13 arc minutes. I think the worst one I've got is like 1.7 or something.
Ruhif, let me show you something, my dude.
Yes.
Let me show you something. Let me show you what the globe predicts.
Oh yeah,
real
show them
quick.
that diagram. I don't think you've seen this yet.
No. Not the diagram. We're going. Ruhif, let me show you what the globe predicts, my man. This is from Spherical and Practical Astronomy from William Chavant. He makes Chauvenet, thank you, sir. He makes the following statement about occlusions and using the timing difference to derive sidereal time if you only know your local solar time. 1 second, I have to turn my phone alarm off. Okay. He saith here that for zenith distances that aren't so great, you can just use the time of occlusion. Basically, you don't have to account for any refraction stuff. But when there is refraction, you have to make a correction because what they're doing, they're referencing the alignment between whatever their terrestrial feature is and the star's true position. So at a high zenith distance, when refraction's basically in the, sub 1 arc minute in difference, that time is just as good. But as you get lower in the horizon, you're going to have more refraction. So they're going to need to subtract that amount of refraction to determine the star's true position.
When it says terrestrial object.
Yeah.
Do you think that terrestrial object is a mountain?
Well, you could do a bit in what they're doing at the angles. You could do a building. You could do a mountain. It doesn't matter.
Yeah. You do a building, you don't do a mountain.
Is there a difference between using a building or a mountain to occlude? Only angle and distance.
You're using a mountain, it implies a very long distance and therefore, a variable refraction in between.
Well, let's see. We've done.
We're talking about something close.
You could be close to a mountain. We've done a 10-degree occlusion or emergence actually, but the angle aspect of it irrelevant. The important part is you subtract the refracted amount to get the true position at the observer location. So when you say that we're strawmanning the globe, you're completely incorrect. This occlusion, observer-centric location, if you were to see the occlusion occur, subtract the refraction out, you would get 206. Well, to get 206, the star had to already be geometrically aligned with the peak at 1842.04. So we're not strawmanning the globe at all. That's false.
Yes, you are.
No, that's false.
Do you put the observer on the mountain?
For the flat Earth aspect, yes.
So what do you
do? That's nothing to do. Observer-centric prediction alignment. The same way that the French did it.
We put the observer at Heffron.
Yeah.
Put the observer at Heffron, right?
Yeah.
Yep. And we have terrestrial refraction to the mountain, which is about 2 arc minutes in that case.
What are you talking about, bro? This is geometric alignments.
You said you're not strawmanning the globe.
Geometric alignments. Do you think the French accounted for terrestrial refraction in this? Do you think that's a factor?
Because they're using a building. They're using the next door building. They're not using a 50-kilometer mountain.
they say at large zenith distance to subtract astronomical refraction. You actually don't know the full scope of what they used, and I don't either, as I went to try and find that volume referenced and I couldn't find the exact volume. But you don't know what they use. But what they do say is that they have to subtract astronomical refraction. They don't say shit about terrestrial refraction at the horizon. So irrespective of using a
Because they're
mountain
not
or
looking long distances.
oh, buddy, but they include a thing on what to subtract at a large zenith distance, like Ruhif.
Celestial
This is
refraction, yes.
and this is not.
Yes.
So celestial refraction is removing that is going to tell you the true position of the star. Okay, so saying terrestrial refraction in this case has nothing to do with anything. We're talking about geometric alignments. Okay, so stay on task. Don't try and make it about something it's not. In order for that star to be at 206 for the observer, it had to geometrically align with the peak for the observer at 1842.06. That's not a straw man of the globe. That's an observer-centric prediction as the globe would do it. That's when they were aligned. Now you disagree.
No, it's not how the globe would do it.
Buddy, we're looking at the French
Champ.
who did the same exact thing to get the true position of a star. When we subtract that, when we look at it without that, we get the true position of where it's at. So there's nothing wrong with what we're doing for comparing geometric alignments. That's not a straw man of the globe.
Okay. They're using a close object. They're not using a 50-kilometer mountain.
Have you read that paper?
How far would you have to go to?
Okay,
Ruhif. In order for there to be a great zenith distance for it to matter, you have to be like sub 20 degrees sub 20 degrees. Otherwise it's going to be like, sub 1 arc minute. Okay. So they're at least far enough away for 20 degrees of something. Okay. Bare minimum. Cause that's what they say. Now
the building across the road is 20 degrees, Alan.
Dude. And knowing the amount of refraction to subtract is all you need to know to get the star's true position, true or false.
Yeah, celestial refraction, yes.
Exactly. That's it.
Yes, we agree. Cool.
Great. So so now you understand that the star was geometrically aligned with the peak for the observer at an earlier time.
Yeah, but you've moved the observer 50 kilometers.
I haven't moved the observer at all. No. That is not.
So let's go.
No, stop. Hold on. Whoa. Let's back up a second. You just said you moved the observer 50 kilometers. Never done that. The observer-centric position is done from observer location, and that's what makes the timing difference earlier, because it aligns geometrically earlier. That's my position. That's it. Just do you understand that now?
Sure. Globe. All right. So the globe, the observer is at Heffron's house. All right. And there is 2 arc minutes of terrestrial refraction to the mountain. All right. And on a globe, that's 217 up to 219. Cool. We agree so far?
Sure.
Oh, hang on. Cool. And the star. Oh, shit. It's here. Give me 1 second.
Bro, even being aligned at 219, that's still an earlier time than what the occlusion actually was.
So mountain at 219 on the globe. The star geometrically is at 206, and there is 13 arc minutes of celestial refraction at 219.
You're looking at celestial refraction.
Agreed?
Yes.
Yeah, cool. So the star is at 219 and the mountain is at 219 at the time of occlusion. Globe confirmed. There we go. I got it right.
That's not a geometric intersection. Why would you do that and then not talk about
atmosphere, Alan? Yeah.
Dude, that's so sad.
I wish there was someone better to talk to than that fucking guy.
I don't know why, but I expected more from Ruhif, but I probably shouldn't have.
No, dude.
No, we got exactly what we expected from Ruhif. Sorry if I'm loud.
No, it's fine. Don't talk about him while he's not here. It's whatever. But anyway, no, this is not a straw man of the globe at all. Subtracting the refraction position gives you the true position of the star. That's what we're interested in. Geometric alignments, the cause of the occlusion. We've been over this ad nauseum. to do all that rigmarole to turn around and be like, oh, let me use the refracted position and dip. Nice, dude.
False
Yeah, that
alarm
was
limit.
so dishonest what he just did at the end there. Yeah, Ruhi, if you're still here, that was pretty shysty what you did at the end there.
What was that?
Globe confirmed and then just
Completely
bounced
ignore
out.
the geometric
Yeah,
alignment.
hilarious.
Not, you know, I'm not strawmanning the globe. No acknowledgement of that. Acting like using an angle at 20 degrees versus a lower angle when you have the amount of refraction is like you're saying that's a strawman of the globe, even though it has the position that lines up with where the quote unquote globe predicts it would be, but we're somehow strawmanning it. Like, you're ridiculous.
We got 219 for both the mountain and the star at the time of occlusion. That's a match for the globe.
Using a different alignment, and also not even the dude, and then that
Using an optical alignment. It's a fucking optical observation.
the occlusion number one doesn't occur with respect to that. Because
Yes, it does.
in other okay, so when you go to Jesse's measurement and you predict that you would already be 3 arc minutes over the peak, that didn't occur, and that's 17 arc minutes off the refracted position. Like, the whole refracted position
Who
is
predicts
in
that?
the globe. The amount of refraction
Gotta
there
zoom in on
is
your
20.
screen share.
The amount, what? The amount of
way.
refraction. Who? What's up?
Your screen share is kind of. Oh wait, never mind. That's my bad. I didn't even know you could zoom in on it.
How about I put the globe prediction for Jesse in the chat?
Dude, go to the
look at that,
observer.
less than an arc minute.
Go to the observer location. Enter the amount of celestial refraction, and it predicts that it would already be 2 arc minutes and 40 arc seconds over the peak.
Now, I've got it on screen. I've set the observer location to where he actually was, and I've set the time of occlusion. Oh, Jesse's here. Hello. And it's 46.4 arc minutes in stellarium, and the globe angle to the peak is close to 46 arc minutes. Less than an arc minute error.
Yeah, where's the true position?
But
I'm going to say the globe works.
Ruhif,
I don't care where the true position is.
Ruhif,
Oh my god, dude.
yo, if you want to do a presentation,
You can keep
on
strawmanning it. Go ahead.
Hey, you're not going to come here and talk over me. Do a different method, and then talk about how, like, what we're doing is wrong or whatever. You can do your own celestial theodolite presentation on what the celestial theodolite isn't on your own time. So check this out. The amount of refraction reported there for the apparent position, 25 arc minutes, puts the true position at almost 46 arc minutes. It's 45.50 arc seconds. Okay. The geometric angle to the peak is 43 arc minutes for the globe. Okay. The refracted position is almost 3 arc minutes over the peak at that time. Now, this continues on for all of the measurements here using the refracted position. Inconsistent here. Now, when we go to something like North Peak as well, 3 arc minutes over the peak, there's no consistency to what
He's got a different elevation.
of what is being said. Oh, yeah, so for all the stars that occluded or whatever, there's different elevations. So I have the
Yes, 659.
I have whatever elevation Jesse has on his spreadsheet. Because I went and got them from
So
there.
Jesse, which one is it? Is it 659 or 631?
So here we go. 1 second, I'll pull it up.
Hold on, let me talk to Jesse. Thank you, Ruhif. It's his measurement, right? Which one is it, Jesse?
Which one is what? I just got
What
here.
is the height? What is the height of what's the elevation height? Is it 630? Is it 659?
What are we talking about? What's the context? The height of
Mountain.
what?
Real quick, we'll just settle this. Okay, HD 187663. I have 650. And let's see, HD 336. He's got elevation. That's in feet. So feet to meters. 650. So this is correct. And
Yeah, they did not all
and
occlude
1
on the
second.
peak.
1 second. Yeah, and I don't dispute that at all. I'm just saying what my spreadsheet shows for your measurements represents what you have on your spreadsheets. Like, I don't know what Ruhif is like doing or talking about or whatever, but everything I have on mine is represents what you have on yours. So you have 231 for skull. I have 231 as well. And same for the,
631, but yes.
or yeah, sorry, 631. But yeah, I have the same for Old Blend as well. Whatever these two are, these will also match.
The light on that is 712 meters. I have used that as a reference point in the image to work out the elevation of the star in meters, or the elevation of the mountain where the star comes out.
You're doing your own thing. You're not actually representing Jesse's
Cool.
information.
I'm doing it accurately.
Well, different thing, and also using a position that we're not considering, and also the we're only interested in geometric alignment. So like I said, if you want to do your own presentation on what the celestial theodolite isn't, you can schedule that with Geo.
Cool. And if you want to keep storming the globe, do it another 36 times. Have fun.
Yeah.
That's all they have, dude. That's
Reduce to rhetoric,
crazy.
dude.
Yeah.
Reduce to rhetoric. Well, anyway, if there are any questions about the central angle gamma relationship,
Dude,
otherwise,
at first you didn't even look at the measurement, dude. You didn't even look at what he presented as a rebuttal, and you just wanted to call it retarded. You're not in here in good faith. Go away.
and then when shown that the technique was used by the French, somehow it's still invalid because the distance is longer and they didn't use a mountain. Like, all right, dude.
Oh, he's talking.
Oh, well, in any case, I'm going to wrap up for the night.
I just had to mute.
Yeah,
Okay.
you're good.
Yikes.
I thought Alan was doing the presentation, not Ruth.
I couldn't have you guys over talking each other. I had to mute you, Ruhif. Sorry. But not
Yeah.
sorry.
All right, lads. Well, we will wrap up and we'll be back next week.
Something real quick, Alan.
Yeah, go ahead.
Okay, just for the French, can you go back to the French paper thing?
The French, yes.
Chauvenet. Just want to make sure I understand this correctly. So they're looking at a star. It gets occluded by a tower, mountain, doesn't matter. It gets occluded, right? And they say that depending on what angle you're looking at the occlusion, right? There's a certain calculated amount of refraction that is calculated. That exact amount, if you remove that exact amount from the actual angle that you saw the occlusion happen, then that's how you get the true position of the star. Is that correct?
Yes. You get the
okay. So
yeah.
Okay, so if that's the case, right? If we were to look at an occlusion of a star, let's say Pike's Peak, we're looking at the star, all right? The apparent position of that star from 231 would be 245 or 244, 245, whatever. So subtracting the amount of refraction would give you the true position of the star, correct?
From the peak, you said?
From the peak.
If you were on the peak, the refraction would from the peak. Well, I guess you
I'm
could
not saying I know that. I'm just saying that if you calculated it, right, the true position would be
yes.
the apparent position minus the refraction, right?
Yep.
Oh, and lo and behold, it matches the occlusion time. Oh, coincidence.
Yeah. So, like I said, it's all about geometric alignment. So for the globe, they would predict from observer for their alignment because the mountain's already dropped and the stars dropping, following 60 nautical miles per degree. as time goes on. So it's going to, like the true position is for them is going to intersect at that earlier time. Whereas on a flat Earth, the angle is going to, it's going to occur later because it has to align with the peak rather than the observer-centric prediction. So, which makes a congruent triangle from star to peak to observer with the flat Earth rise over run to the peak. That should be geometrically impossible on a globe. The only way the globe could have it is if it was at an earlier time, because then that would satisfy their geometric alignment.
Before you end it, though, Matthew Learns, are you there?
Yeah, I'm here. How's it going?
What's up? I prefer talking to you as like a steel man. Do you understand kind of what Alan is putting forth when he talks about the geometric alignment to the true position, the star?
I don't understand the math, no, but I understand what he's trying to say, that that we can somehow find out where the true position of the star is. But the interesting thing is that 69 degrees, 69 miles per degree is a linear equation.
Right? But in order to keep that linear equation intact, right, when you start getting, anomalies like stars basically still above the horizon at certain angles, right? That's where you have to incorporate celestial refraction in order to keep that ratio intact.
Well, yeah, so that's why I'd say, like, look at all the stars above 20 degrees where there's the refraction doesn't play much of a role. And the point is that it's still a linear equation from 20 degrees up to 90 degrees.
Yeah, but below 20 degrees is what we're talking about.
Yeah, I don't know much about what happens below 20 degrees. Because once you start doing all the complicated things of like atmosphere, refraction, all that stuff, who knows? Depends on atmospheric conditions and temperature and pressure and humidity and all that mess. But I'm saying that oh, sorry, go ahead.
No, I was gonna say none of that is actually incorporated when you actually take positions of stars. For example, with stellarium, if you, like Pike's Peak, that star, should have occluded earlier, according to the globe geometry.
Yeah, I don't know about that. I'm just saying that the fact that we have this 69 degrees or 69 miles per degree, that equation by itself is problematic if you're trying to do triangles, because it's a linear equation, and triangles don't have linear equations.
Sorry, could you repeat that last part? I kind of cut out.
Sure. If you're looking at a star, and let's say it's all above 20 degrees, like from 30 to 40, then 40 to 80 or whatever, the distance to that GP is 69 miles per degree, and that equation is a linear equation, and linear equations don't appear in right triangles.
But what do you do? What happens when you get down to below 20 degrees?
I have no idea. That, like I said, that's a complicated mess of refraction and humidity and temperature and pressure and all that.
So, why we would want to use stars that low to the horizon, because then it would show the actual difference between flat and globe, right?
I don't think so. I think the fact that it's a linear equation is sufficient. And if you're doing celestial navigation, you try to ignore those low stars anyway, right?
Dude, irrespective of them being low in apparent position-wise confusion, the true position is following the 60 nautical miles per degree plus or minus latitude variation. Like, otherwise it doesn't complete a circle in 24 hours. So I don't know exactly what you think you're contending or whatever or saying, but,
Oh, I see. So you're saying the true position still follows that 60 nautical miles per degree?
Yes, that is the backbone of the globe. When they do celestial navigation, that is the position that they're referencing that defines the GP for the star. That's why they...
And it works, right?
Yes. It's a calculated position that's internally consistent. So of course it's going to work. But the point is, does it work or not? The point is it follows that relationship, which you were saying that it didn't. And then it like, I don't know what you were confused about, but you seem to be caught up now. The 59.
Oh, no, I was never confused. I still say it's a linear equation, so it can't be triangles.
The fuck? All right, dude. We know this. We know the star's position and time. That's all we need to know to start a vertex for a triangle, where the star once was. What you're describing and relating to a triangle is not relevant. All we're saying is that we know where the star's true position is at any given time, right? Correct.
Yeah, we know where that is. Right.
All right. That's all.
The almanac knows where it is.
That's it.
And 60 miles per degree from the zenith distance. That is a multiplication, a simple multiplication, which means it's a linear equation.
Okay. And how's it mutually
Linear
exclusive?
equations do not appear in triangles. They're trigonometric equations.
Okay.
So
what's your point?
Not going to triangulate. My point is that right triangles have nothing to do with celestial navigation.
Who's doing celestial navigate? Like, dude. All right, Matthew. It's been.
I confirm I do celestial navigation.
Nice, dude.
I thought we were talking about a celestial theodolite.
We're talking about knowing the stars and the linear and non-linear triangles has nothing to do with what we're talking about.
Yeah, we're not doing celestial navigation.
Per se.
Yeah. I'm just saying that the thing you keep referencing, 60 miles per degree, that right there is a simple multiplication.
So, in other words, nothing of significance. And I hate to be rude, but it sounds like you're literally saying nothing.
I'm saying that kind of linear equation is well explained on the globe model, but it has nothing to do with right triangles on a flat Earth.
Just rhetoric.
I know it's mathematics, not rhetoric.
No,
Do you
if
even
we know
understand
the
what's being
star's
presented?
angle at the time of occlusion, we can make reference to that angle. And we could reference where that star would be aligned with respect to the peak or with respect to the observer. Like, it's an interesting contention, Matthew. Thanks.
And the celestial theodolite method doesn't even work.
The celestial theodolite method doesn't even work. Quote from a guy who went to a spot where the flat Earth true position overlaps with the apparent position to try and get a measurement, so that to my face you could say that you did our method by true position alignment, and talking to Globe Lads you could say you did your own method aligning the apparent positions. Like, and even when we go through those, none of those